Good evening. My name is Robert Dijkgraaf. I'm the director and Leon Levy professor at the Institute here, and it's my great pleasure to welcome you to this Institute lecture. And as always, we will have a lecture and then we'll have a question and answer session afterwards to address all the issues that will come up, and of course there will also be a reception in the common room in Fould Hall that you all are cordially invited to. I'm very happy that today we have as a speaker Nathan Seiberg, professor in the Institute's School of Natural Sciences since 1997. And Nati has been a member of various kinds, visitor, so I think he has a full experience of Institute life. He is a leading theoretical physicist whose research has made major contributions to our understanding of particle physics, quantum field theory, and string theory. And I think it's his seminal work on the dynamics of supersymmetric quantum field theories, which some of it did in close collaboration with his colleague here, Edward Witten, the Charles Simonyi professor in the School of Natural Sciences, that Nati has initiated an entirely new period in theoretical particle physics. I would say many phenomena that were heuristically explored could, through his insights, certainly be found and studied in exact solutions, often of profound mathematical elegance and originality. And this new perspective led to the uncovering of many new and unexpected insights. For instance, the fundamental role of electric-magnetic duality, quark confinement, and many, many different other things. It's a word that's usually overused, but I would say it led to a real paradigm shift in our understanding of quantum field theory, of particle field theory, where an archipelago of different particle models basically became united in the form of a vast landscape of different phases of some underlying theory. And I think that point of view that started with Nati's work has fundamentally impacted our view not only of quantum field theory, but string theory, condensed matter, quantum gravity, many areas in theoretical physics and also mathematics. But that work was not only important for pure conceptual relevance. Nati has also clarified how supersymmetry can be dynamically broken and tested, and what its implications are for the many experiments that are now underway that you all read about, for instance at the Large Hadron Collider in CERN Geneva. Nati earned his PhD from the Weizmann Institute of Science, where he also worked as a senior scientist, an associate professor and professor. And additionally, before coming to the Institute, he was a professor of physics at Rutgers University. His extraordinary contributions to the field have led to many awards and honors. I just mentioned a few. In 2012, Nati was one of the 4 Institute faculty members to receive the inaugural Fundamental Physics Prize. Other awards are the MacArthur Fellowship, Oscar Klein Medal, the Denny Heinemann Prize, very prestigious too, from American Physical Society. And he's a member of various learned societies, mentioned the American Academy of Arts and Sciences and National Academy of Science. Nati's style of lecturing and his whole work is always very crisp and clear. I'm just setting up expectations here. And your title is similarly crisp, what's next? In fact, that's a question that, a title that captures a lot of what's being done here at the Institute. And you promised to have a look at the possible new physics beyond the standard model, and how that's relating to the exciting experiments that are going on, and that we do feel that in the past, in the present, and in the future, the Institute plays a very important role. So please welcome me, Nati Seiberg, to the stage.
Thank you. Thank you, Robert, for this wonderful introduction. I'm afraid after such an introduction, there's only a way of stepping down and you might be disappointed. Thank you, all of you, for coming, and I hope you will not be too disappointed. Before I start, I would like to say something about the title. It's kind of a disclaimer. I do not know what the future will bring. I guess nobody knows. And we do not know what will be discovered, either experimentally or theoretically. And that's actually one of the reasons we perform experiments. If we knew for sure what the outcome of the experiment would be, there would be no reason to perform the experiment. This is also the reason scientific research is exciting. It's exciting because we are constantly surprised, either because an experiment has an unexpected outcome, or theoretically somebody comes with a new insight. So what we'll do today, if we want to plan for the future, we have to discuss first the past and the present, and I guess if there are historians in the audience, they are not going to dispute that. And what I'll do today is to give you a status report of where we are in fundamental physics, what we understand, what we do not understand, and I will also share with you some of the excitement of the coming years. So like the news, I'd like to start with a summary. We are in an unusual and almost unprecedented situation in physics. We have two standard models, one of them describing the shortest and one of them describing the longest distances in the universe. And these models are quite spectacular. They work extremely well over the range of distances that they were designed to work. And we do not know of any contradiction with these models. So this is quite amazing and almost unprecedented in science. However, there are excellent arguments that this story is not complete. And there must be new physics beyond these models. So what I'll do in this talk is try to summarize some of the historical background, summarize these models, and then outline the open questions, and then what the next step could be. So I'd like to start with comparing it with a similar situation in science, which happened at the beginning of the 19th century. A famous British physicist, Kelvin, you all know about Kelvin degrees, gave a lecture called 19th Century Clouds over the dynamical theory of heat and light. So during the 19th century, physicists devised a beautiful theory of heat and light, which explains a lot of phenomena. And the consensus among physicists was, we really understand everything, and perhaps we are near the end of science, because everything is understood. And what Lord Kelvin said, there are few clouds over the horizon. And these clouds were really the beginning of the sign of a big storm that completely changed our understanding of physics and of nature more generally. And these clouds were the Michelson-Morley experiment, which eventually led to the theory of relativity. And the other was the black body radiation, which eventually led, among other things, to the quantum theory. So this is an interesting setup where we have something that works almost perfectly. There are only a few details that don't work, and the details really should be interpreted as the first sign of the next revolution. So some people interpreted this to mean that physics was almost over. In fact, you will often see on the internet or elsewhere people writing about Kelvin. He was so naive, he thought physics was almost over. There were only these details that are not understood. But in fact, if you read what Kelvin actually wrote, Kelvin said that these should be clues that one should focus on. One should focus on these little discrepancies, these little things that are not fully understood, because these are the things that will guide us to the next revolution. So what I'll do today, I'll give again, as I said before, I'll review the current state of fundamental physics, and I'll review today's clouds. What are these little details that don't quite work, and say that these are the ones that we should be focusing on, the ones that will guide us to the next point, to the next revolution. In order to keep track of what I'm doing, what I'll be doing in this talk, I would like to present a theme that we'll go through again and again in this talk about how scientific research works. Not all scientific research works this way, but in many cases, we have a situation like that. So we often research progresses in steps. So step one, we collect data, a lot of data. And then somebody smart looks at the data, says, oh, here is a pattern. We can explain a lot of numbers using fewer numbers. We refer to these numbers that we cannot predict. We have to measure them as the parameters. So we measure a small number of parameters, and then we have some formula or a pattern, and using this small number of parameters that we measure and the pattern that we have, we can predict many, many other numbers. So this is the way we make progress. We explain many numbers in terms of fewer numbers. The next step in our understanding, we ask to ask, why is the pattern right? What is the underlying principle that controls this pattern? We found the pattern experimentally, and we'd like to understand the underlying principles behind it. After we understand the pattern, so after we understand the underlying reason, we still have these parameters that we have to understand. Where did these numbers come from? At this step, we start collecting more and more of these parameters. We call this is the new data, and then we go back to the beginning, and the cycle continues. And there are many, many examples in science that are like that. And what I'll do in the next few slides is present two historical examples that we can learn many lessons from them, where we'll see exactly this pattern of collecting the data, finding the pattern, the underlying principle behind the pattern, trying to understand the remaining parameters, and going back to the beginning. So the first example, first historical example, is the motion of the planets. From ancient times, people were fascinated by stars and their motion. And here is a picture from Babylonian times and then some Greek astronomers. So they started collecting data, trying to see how the stars move on the sky. And they devised very complicated and sophisticated models known as epicycles, where we have circles within circles within circles. It was quite complicated until the true pattern emerged. And the true pattern is the heliocentric model of the solar system, where the sun is in the middle and the planets circle around the sun. A lot of numbers could be summarized in terms of far fewer numbers. Instead of knowing the complicated motion of the planets, instead of that, we have small numbers of parameters like the radii of the orbits and some of the phase of how all these planets move around and so forth. So this was mostly through the work of Copernicus, Galileo, and Kepler. So again, a lot of data. The data was summarized in a pattern, and at the time of Copernicus, Galileo, and Kepler, the pattern was understood, but the underlying reason for the pattern was not understood. And we had these parameters that Kepler had to measure, which are the radii of the orbits. Now, Kepler wanted to understand this pattern. Where did these radii of the orbits of the planets come from? And he noticed that at the time, six planets were known, and he tried to relate that to the 5 Platonic solids. The Platonic solids are these perfect shapes that the Greek were fascinated by: tetrahedron, cube, octahedron, dodecahedron, and icosahedron. And Kepler's idea was that the stars move on these spheres, and we have spheres which are inscribed in, we have inside them, say, the cube, and here is another sphere, and this is the tetrahedron, and so forth. Altogether, we have 6 planets inscribing 5 Platonic solids. And that looks very deep. Beautiful mathematics, very deep, the fact that we have 5 and exactly 5 Platonic solids. And this is correlated with something in nature, the fact that there are 6 planets. Well, this is all very nice, except that it's completely wrong. It's completely wrong, first of all, because the planets move on ellipses rather than on circles, so they're not on these spheres. Second, the numbers don't quite fit. Later, Kepler himself realized that the numbers don't quite fit this beautiful theory. And the real thing that killed it is that there are more than 6 planets. And there are no more than 5 Platonic solids. Today, we understand that these numbers, the radii, are not fundamental. And we should not be looking for a theory explaining these numbers. These numbers don't have any deep truth. These numbers originated in the time the solar system first created, and they could have very well be a little bit different. If we look in the sky, we find other solar systems in the sky, and in these other solar systems, there are planets circling other stars, and their radii are totally different. So this is just an accident of this particular solar system we happen to live in. So this turns out to be the wrong question. Wrong question in the sense that it's very interesting to measure these radii. There's a lot of interesting physics there, but these numbers are not fundamental. So this is a lesson we'll face later, that sometimes we try to explain a number which is not fundamental. And the art is to figure out what is it that we need to explain. So we talked about collecting data and looking for the pattern. And the next step, understanding the physics underlying the pattern. Why do the planets move on these ellipses? And this came with the work of Newton. Newton understood dynamics. He understood the laws of motion. He understood the law of gravity. And using these laws, he understood why the planets move on ellipses. So this is the new insight, that the experimentally discovered pattern that Kepler discovered, this pattern is now a consequence of deep fundamental laws, which are also true elsewhere. So we see again this pattern of data, pattern, and the principle. In fact, Newton was quite concerned about one problem here. He knew that if you have one planet moving around the sun, the planet will move on an ellipse. But we have other planets, and we have the moon, and we can have comets, and they also exert forces on each other. So the motion of the planets cannot be exact ellipses. And because of the influence of the other bodies, the planets could move a little bit. And Newton was concerned that this problem of not just one planet around the sun, but several planets around the sun, this problem is unstable. And kicks from the other planets could send some of the planets into a bad orbit. For example, it could send the sun into it could send the Earth into the sun, or it could send one of these planets outside the solar system. There's a beautiful place, you can read about this, a beautiful presentation due to our colleague Scott Tremaine in the Institute newsletter, and I strongly recommend it, that you look at it. So Newton was concerned about the stability of the solar system, and this is again something, we have parameters. One thing we have to worry about is, are these parameters stable? So, and we'll see that later in the talk. So Newton faced this problem, and he asked himself, how come the solar system has been around for so long, even though it appears to be unstable? And his solution, Newton's solution, this is described here in the words of the historian Hoskin. God demonstrated his continuing concern for his clockwork universe by entering into what we might describe as a permanent servicing contract for the solar system. So Newton's idea was that the solar system is unstable and some of the planets might move from these perfect orbits. So occasionally we need divine intervention to come from the outside and put the planets back in their orbit. If you think of it, it's really amazing that after he figured out the laws of nature and how the planets move, and after figuring all that, he thought we need an unnatural explanation of these unstable numbers. And this theme of unnatural explanation for unstable numbers will come later in the talk. Whoops. So today we know that Newton's concern was really unjustified. It was unjustified because the solar system is a lot more stable than Newton thought, and there's been a lot of work, including here at the Institute, exploring the stability of the solar system. This is connected to chaos. It's really a fascinating topic that I will not get into. So this is my first example where we see how the pattern works of collecting data, looking for the pattern, and then looking for the principles. The next example is the development of chemistry. And again, this started in very ancient time. People were very interested in materials around us, and they started collecting data. And they've collected a lot of data, properties of materials, and so forth. People often mention the alchemists as being people who did misguided research. And again, there's a very interesting, useful lesson to learn here. The alchemists wanted to create gold out of ordinary materials. That was misguided. They failed because this was the wrong question to ask. Nevertheless, they generated a lot of useful data. They learned a lot about materials. They learned a lot about, got a lot of information about chemistry at that time, and that was useful later. So this is the step of collecting the data. Then comes the next step of looking for a pattern. That took several centuries later, and the pattern came with the work of Mendeleev. He understood that some of the materials are elements, and using the elements we can construct compounds. And the thing to organize is to focus on are not the compounds but the elements, and the elements can be arranged in such a beautiful periodic table. This is the pattern. Oops. This is the pattern. Actually, at the time of Mendeleev, there were many gaps in the table, so it was much more challenging to figure it out. By now, there are no gaps. And this is a beautiful story, which is very helpful for chemistry. And that brings us to the next step. Collect the data. We've talked about that. Figuring out the pattern. And then the question is, what's the underlying reason for the pattern? What are the fundamental laws that control this pattern? And that came in the development of quantum mechanics, in the structure of the atom and quantum mechanics, at the beginning of the 20th century. So I look for a first timestamp. When can we put the timestamp for the beginning of quantum mechanics? And I think this is the first time, the timestamp. This is the first Solvay conference in 1911. This was one of the first scientific conferences in the world. Before that, there were very few scientific conferences. This is an amazing collection of people, just to mention a few of them: Curie, Poincaré, Planck, Rutherford, and Einstein, and many others who are also quite famous. We'll talk about some of them later in the talk. And an interesting story is that this person here is Ernest Solvay. He's the philanthropist who gave the money for the conference, and he couldn't come to the photo session. So they left a chair open for him, and they took another photo of him later, and they pasted it in. And I think this qualifies as the first Photoshop job. So this is the beginning of quantum mechanics. We want another timestamp, kind of when quantum mechanics was understood, and I think it's fair to put this one. This is the 1927 Solvay conference, and this is quite amazing because it's only 16 years from the first one. If you read the proceedings, it's fascinating because they were totally confused. They asked the wrong questions, they didn't even know what was going on, and by 1927, the story was almost completely understood. So these are 16 amazing years. As you can see, some of these people aged a little bit in these 16 years. And here the list of participants is equally impressive. Let me just mention a few of them: Schrödinger, Pauli, Heisenberg, Dirac, Bohr, Planck, Curie, Lorentz, and Einstein. So this is quantum mechanics. This is what explains the pattern. Now the pattern becomes a consequence of fundamental laws that we understand. This is the Solvay conference. But we still have the remaining parameters. And the parameters, these numbers that we have to measure and we cannot predict, in this case are the mass of the electron, the masses of the nuclei, and so forth. And this is an amazing achievement because using a small set of numbers that have to be measured, like these, huge amount of information can be deduced. And it can be deduced, at least in principle, if not in practice, because the equations are very complicated, but at least in principle, we think we know what the fundamental laws are. So this is the second example. I gave the example of the motion of the planets, and now the example of chemistry. And now I'd like to shift gear and move to the two standard models. So we have two standard models. They were developed during the past few decades, second half of the 20th century, maybe a little earlier than that, till today. And one of them is in particle physics. It addresses physics at very short distances, 10 to the minus 19th of a meter. So it's 1/10 of 1 billionth of a billionth of a meter. And this model is in perfect agreement with experiment. The second standard model is the standard model of cosmology. It's again a nearly perfect model that describes the universe as a whole. It goes up to distances of 10 to the 26 meters, the entire visible universe. Notice the huge scale of distances that we talk about. These are unimaginably small, and these are unimaginably large, and yet we think we know what the fundamental laws of physics are in this entire range, which is quite an achievement. Again, in many cases, we understand the laws only in principle, and what most physicists do is try to understand the consequences of the laws we understand. All of chemistry follows from these laws. All of biology follows from these laws, and there's a lot of interesting, exciting science trying to work out the consequences of these laws. But at least in principle, we know what the fundamental laws are. So let me say a few words about every one of these models. So the standard model of particle physics, and again, we have to remember what are the principles, what is the pattern, what are the parameters, and so forth. So we'll have to always to keep in mind this theme of the talk. So we'll start with the principles. The principles of the standard model of particle physics are these two of the revolutions of the 20th century, quantum mechanics and special relativity, and they are combined into the subject of quantum field theory. The next topic is the matter particles. We have electrons that were discovered earlier, and quarks that were discovered more recently. I'll talk about them in the next slide. And we also have forces. The electromagnetic force was discovered and fully understood in the 19th century, and two 20th century forces, the strong nuclear force responsible for nuclear energy, and the weak nuclear force responsible for radioactivity. And we have the parameters. The parameters are these numbers that the model cannot predict, and we have to measure them. These are like masses of the particles, the strength of the forces. So I'd like to say a few more words about the matter particles. They come in a table like that. The quarks which are inside the proton and the neutron. There are 6 of them, up, down, charm, strange, top, and bottom. And the electron is also a member of another family, again, 6 of them, electron, mu, and tau, and every one of them has a particle associated with it called neutrino. So here we see a table. Some properties are the same along the column. Some properties are the same along the rows, like all these particles have the same charge. And we can call this the periodic table of matter particles. Well, history starts like we've seen that before. We have a pattern of elementary objects, and it really asks the question, where did this come from? Why do we have this pattern? And the answer is that we don't yet know. So this is one of the puzzles we would like to understand. Why do we have this pattern? It's clearly there, and there's something to understand. The last piece of the standard model that was discussed is the Higgs particle, the discovery of the Higgs particle. This is a particle that gives masses to other particles. It was discovered in 2012 at the LHC, the Large Hadron Collider near Geneva. And I'm not going to discuss it in detail here. This is a very interesting story, and I recommend you look at on the Institute webpage, where you can find a beautiful talk by Juan Maldacena, I think about a year ago, where he describes it here. So I'm not going to talk about that. This discovery was recognized by the recent Nobel Prize in Physics that was given to these 2 people, Angler and Higgs. This is a picture of them in the press conference when the Higgs was discovered. And Robert just pointed out to me this morning, just before the talk, that we're wearing the same tie. This is not completely coincidental. This tie was actually designed by a famous Nobel laureate. This was a gift he gave to the guests in his 60th birthday, and I think Robert has a similar tie. I think he was one of the organizers of that birthday. Yes. Good. I think it was your thesis advisor, right? Good. At Hoft, Gerard at Hoft. Thank you for asking that. Okay, so the significance of the Higgs discovery is that now we know not only that the standard model is right and it's complete, but also that its mass is the last parameter of the standard model. So now we know all the parameters of the standard model. We can measure them more accurately, and we can have a lot more fun. We can test the model more accurately, but we basically know all the equations and all the parameters, everything we would like to know about the standard model. So if it's so nice, what's bad about it? So the standard model is extremely successful. We have the order of 18 parameters. There are 18 parameters. And using this small number of parameters, like the mass of the electron, a lot of quantities can be calculated and measured. And there's remarkable agreement between theory and experiment. First, there isn't a single contradiction. I'll qualify this a little bit later. And second, we have an unprecedented success. Most objects cannot be calculated or cannot be measured. And some of them we can calculate only approximately. But some quantities can be calculated to enormous accuracy, up to 10 significant digits, and they can be measured to the same incredible accuracy. And the 2 numbers agree. There isn't a single example in science where a theoretical prediction and an experimental measurements match to 10 significant digits. This is quite impressive, and it really shows that we know what we are doing, the model is right. And there is ongoing effort to try to improve the accuracy, both on the theory side and on the experimental side, hoping that at some point we'll find a discrepancy that will be a clue, kind of the new cloud. This discrepancy will be the new cloud or the new clue to the next step in science. So what are the open problems? Using Kelvin's terminology, what are the clouds over this model? The clouds that we should view as clues for the next step. First of all, the standard model exhibits a pattern. I've already described this pattern, this periodic table, and we would like to understand it. What is the origin of the particles? Why do we have these particles and not others? What determines it? We talked about the forces. There are 3 forces. Why do we have 3 forces and not 4? What determines the strength of these forces? And we have all these parameters, these 18 parameters that we don't know how to predict. We have to measure them. Where did these numbers come from? We would like to understand them. Finally, within the standard model, we have the Higgs particle. We now measure the mass. We know the mass. It's about 133 times the mass of the proton. So we know the mass of the particle, but this mass is unstable in the sense that I will explain later in the talk. We also have one experimental clue beyond the standard model, so I was slightly imprecise when I said that there are no experimental contradictions. The neutrinos, this particle associated with the electron that I had before on the slide, have no mass in the standard model. In the standard model, they have exactly vanishing mass. But experimentally, their mass is non-zero, and it was measured. We know it's non-zero. This is a tiny mass. This is not a complete disaster, because the tiny mass tells us at what length scale the model should break down, at what length scale should we have new physics responsible for this mass. And this distance is a lot shorter than the distances in the standard model. So over the range of distances that we work, we know what we are doing. This is not really a problem, but this is clear experimental evidence that there must be new physics, and the standard model is incomplete. This is what I wanted to say about the standard model of particle physics, and let me say now a few words about the standard model in cosmology. This is a long and beautiful story that I will review here only briefly, and more details can be found again on the Institute website. There are excellent talks given by Matthias Zaldarjaga, where he gives a lot more information. So where do we get the information about cosmology? We get them from many sources, primarily from two sources. One of them is two satellites, the Wilkinson Microwave Anisotropy Probe, in short WMAP, which has a very large Princeton component. And the second is the Space Telescope of the European Space Agency. And these experiments look at the sky, and they measure microwave background radiation, microwave radiation in the sky. One of the fundamental things in cosmology is that we had a Big Bang, an explosion that generated the universe, and one of the echoes of this explosion is this microwave radiation in the sky. And these satellites look at the sky in various different directions, and they see that the radiation is not exactly the same in every direction. You see that there is a certain pattern here. And they look at this pattern of the radiation in a lot of detail, and that gives us a lot of information. These fluctuations give us a lot of information and tell us a detailed story about the evolution of the universe. The second source of information comes from survey of supernovae. Supernovae this is the plural of supernova. A supernova is an explosion of a star. It's an explosion which is extremely energetic. It can outshine the galaxy the star is in. And it's so powerful that we can see the explosion in the entire visible universe. We can look at all the way to the edge of the visible universe and see these supernovae that explode there. And these three people measured how fast these faraway supernovae recede from us. And they found out that not only do they recede from us because the universe expands, but the expansion of the universe accelerates. So this was a big thing, which was recognized in 2011 by the Nobel Prize in Physics, that the universe accelerates. So using all this information, we get a complete picture of the whole universe, and summarized by the standard model of cosmology. And again, we have this structure of principles, and some data, and some parameters. So the principles are general relativity, the other revolution at the beginning of the 20th century, and the Big Bang, this explosion in the early universe. And then we have the composition of the universe. These are the latest numbers from the Planck satellite. Notice that only 5% of the total budget here is ordinary matter, matter like the matter that we are made of, matter described by the standard model of particle physics. And the vast majority of what we have is something else, which tells you that there's still a lot we don't understand. About a quarter is dark matter. This looks like other matter, very much like ours, but matter we haven't seen before. We don't know what it is. And about 70% is dark energy, responsible for this expansion, or responsible for this acceleration in the expansion of the universe. So altogether, we have again a situation somewhat similar to what we have in particle physics. We have a handful of parameters, 5 to be precise. And using these 5 parameters that we have to measure, a lot of information can be predicted, a lot of information that agrees with experiment. So it's again a spectacular success. A handful of numbers predict a huge data set. There isn't a contradiction, and we have a beautiful and coherent picture of the universe. So what is it that we need to understand? What are the problems? One of them I've already mentioned. What is this dark matter, this mysterious matter that is everywhere, and there's a lot more of it than the matter we are made of. What is this dark energy? This is even more puzzling, partly for reasons I'll mention later. And again, what is the origin of the parameters? Where did all this percentage of how much dark matter, dark energy, and so forth, where did these numbers come from? And then there's the issue of cosmic inflation. Very early on, right around the time of the Big Bang, if you wish, a little bit before that, there was a period of very rapid expansion where the universe expanded much more rapidly than it expands today. And there's a lot of evidence that this is right, but there are still many puzzles, and this is something that we need to understand. So these are the two models, and these are some of the puzzles, but we also have the biggest conceptual puzzle. And the biggest conceptual puzzle is to merge the two standard models. We don't want to have two standard models, we want to have only one standard model. We would like to merge these two models. And one of these models, the model of particle physics, uses two of the revolutions of the 20th century, quantum mechanics and special relativity. The second model, the cosmology model, uses the third revolution of 20th century physics. This is general relativity. So we will need to combine the principles of one model with the principle of the other model. In other words, we need to combine quantum mechanics and general relativity. Where should this happen? What's the characteristic scale? The characteristic scale for that is extremely short, and it's known as the Planck scale. And this is Mr. Planck, who was also in these two Solvay meetings, just to show you that this is something that was understood long ago, over 100 years ago. Planck understood that quantum mechanics and general relativity, or quantum mechanics and gravity, should become important at tiny distances, 10 to the minus 34 meter, unimaginably small, a lot shorter than the scale of particle physics. And in terms of mass, this is about 18 times the proton mass. Slightly more technically, I'm using here what is known as the reduced Planck scale rather than the actual Planck scale, but that's not important. Once we have such a theory, this theory should address the structure of the universe as a whole with quantum mechanics, with shorter distances. So it should address what happens to the universe when the universe was of the size of 10 to the minus 34 meters, tiny universe. So this is really a theory of creation, if you wish. What's the best candidate to answer that? The best candidate is clearly string theory. This is a huge topic for another talk, or maybe more than one talk. And again, I'll refer you to the Institute website, where there are beautiful talks by Edward Witten describing developments in string theory. There are big challenges in string theory. We still don't understand what the fundamental principles of the theory are. We also need experimental confirmation. And I think it's quite clear that these challenges might take a very long time to achieve. Nevertheless, there has been enormous progress with amazing new insights over the past decades, and all the signs are that this activity continues and will continue to make progress, and a lot of that is done here at IAS. But I'm not going to discuss it in any more here. Instead, I would like to focus on what seems like a smaller problem, not find everything, but try to explain these parameters of the two standard models. We have 18 numbers that we see, we measured, we have them in particle physics, and we have these 5 numbers in cosmology. Where did these numbers come from? Perhaps this is an easier question because it's kind of more quantitative. So we have these parameters like the masses of the particles in particle physics, or the amount of dark matter, and so forth. These are input parameters for the models, and we would like to find another model for which this will be the output. There will be something else more fundamental, hopefully fewer numbers, and using these fewer numbers, we'll be able to predict all these numbers. So the existence of these parameters tells us there must be some deeper truth. So we look for such a new model that can predict or can explain the pattern we see in the numbers that we measured in the standard model. Ultimately, we would like to find a model that has no parameters at all. That would be really satisfying, to have a theory that we don't have to measure anything. Everything is predicted just by pure thought from the theory. And this vision was put forward by Einstein, where he said there are no arbitrary constants. Nature is so constituted that it is possible logically to lay down such strongly determined laws that within these laws only rationally determined constants occur, not constants, therefore, whose numerical values could be changed without destroying the theory. In other words, Einstein's vision was that there would be some fundamental equations and there would be some numbers in the equation. 3.7, maybe pi, and so forth. And these numbers are not numbers that we'll have to go to experiment to measure, but the equation itself will not make sense unless these are the values of the numbers. Well, we are not there yet. This is our ultimate goal, but first, so we might achieve this goal in steps. We might find another model that has fewer parameters than what we currently have. But let's focus on an even easier problem. Before we try to explain all the numbers with their precise value, let us just try to understand the qualitative structure. Some numbers are big, some numbers are small. Why is that the case? So we would like to explain the hierarchy between the parameters. So the first parameter to explain is the overall scale. And this already looks quite puzzling. Because I mentioned this Planck scale, the scale where the fundamental theory should be, the scale where quantum gravity is important, these tiny distances, or these high energies, which are about 18 orders of magnitude more than the proton, or about 16 orders of magnitude heavier than the Higgs. Where did this come from? So in other words, imagine we have a fundamental theory at the Planck scale. This fundamental theory should predict a number which is 10 to the minus 16. This is really hard to imagine. Where did such a small number come from? How can we design a theory that after we do a calculation, a number like 10 to the minus 16 will pop out? We know how to get pi squared, maybe 5, maybe 7, but 10 to the minus 16 looks strange. In cosmology, the problem is even worse, because here we have to explain 60 orders of magnitude. The observed universe is big. We know the observed universe is big. The Planck length is small. Where did this huge hierarchy come from? Why do we get such a big universe out of a tiny scale? 16 orders of magnitude, 60 orders of magnitude. Equivalently, why is the scale of dark energy density so small relative to the Planck scale? Actually, for technical reasons, the relevant number is not the ratio between the two masses, but the square of that. And that makes the puzzle even worse, because this becomes 10 to the minus 32, and this becomes 10 to the 120. So we have to explain how we have a fundamental theory with some numbers, and after we do some calculation, the answer turns out to be 10 to the minus 120. This is really hard to imagine how we can find such a theory. In fact, the question is a lot more difficult than that. First, we need to understand the origin of the hierarchy, where these widely separated scales come from. But the second, what is even worse, is this enormous difference in scales is unnatural or unstable. So recalls Newton's concern about the stability of the standard model. There were all these numbers, these parameters that Kepler had, and Newton was concerned that these numbers were unstable. If we kick the system a little bit by Jupiter coming closer to the Earth, or something with a comet passing by, that could completely destabilize the solar system. Similarly here, we would like this ratio between different scales to be stable, in a way I'll soon make precise. So Newton thought that we need some divine intervention. We would like to use more natural means. That's why some people refer to this problem as the naturalness problem. This ratio of scales looks unnatural because it's unstable. So in other words, we would like to ensure that if we change the parameters at short distance a little bit, the effect at long distance is not too big. This we call stability. We make small changes at short distance that will not make too dramatic differences at long distance. So some parameters in the standard models, in both of them, seem unnatural, seem to be unstable. In particular, the mass of the Higgs, or the scale of particle physics, and the dark energy density, or the size of the universe. So let me say a few words about stability. Imagine you walk in the forest, and you find a structure like that. Well, I bet it's never happened. You've never seen anything like that. I stole this picture off the internet, I gotta say. So imagine you walk in the forest and you see something like that. You say, wow, that doesn't make any sense. And of course, you didn't see it. And the reason we think it doesn't make any sense is that it's unstable. So even if somebody arranged this configuration of rocks, the configuration of rocks is unstable. A little bit of wind will knock one of them out. If an animal passed by, it will destroy it. Or if a bird came and just sat on top of it, the whole thing would collapse. So it's unstable, and that's why we don't see it. When we walk at a random time, there was enough time since this thing was constructed for it to collapse. But imagine we do walk and we see such a structure. What will we immediately say? first question may be who put it there, and the second question, why is it stable? And upon reflection, maybe we'll find a mechanism. Maybe these rocks are actually connected to each other, and it only looks unstable, but in fact it's stable. There's a lot of artwork which looks unstable, but the artist just connected the different pieces so that it is stable. We'd like to use all these things and talk about the stability of the hierarchy. So we talked about this hierarchy, these different widely separated scales. And now imagine we have a more complete theory where we can compute these parameters at low energies. We can compute the parameters in the standard model of particle physics, or we can compute the parameters in cosmology. So say the mass of the Higgs. So we want to compute the mass of the Higgs boson, and we have some calculation to do that. Many effects contribute to the mass. All of them are more or less of the same order of magnitude, like the fundamental scale in the theory. In this case, it will be this Planck scale. So there will be many contributions with different signs. Some of them will come with a plus sign, some of them will come with a minus sign. One of them will be 1.3, the other will be a tenth, the other will be 20. And they will come with different signs, and then they will add up to a number which is 10 to the minus 32 in the case of cosmology, or in the case of in the case of particle physics, or 10 to the minus 120 in the scale of cosmology. So as I say here, all of them are of the same order of magnitude, which is the Planck scale, but they have different signs, and they have to cancel these different numbers that come from different places. All of them are of the same order of magnitude, must cancel to enormous accuracy. This looks insane. So this delicate cancellation looks unnatural and seems a lot like the problem that Newton was concerned with the standard model. It looks unstable. And we do not want to use divine intervention. So what we should look for is a natural explanation for this, and that's why it's called the naturalness problem. So this hierarchy is unstable. Small changes ruin the cancellation and ruin the hierarchy. So what are the logical options? We would like to explain this hierarchy, and what are the logical options? Option number one, we are simply wrong. And maybe this hierarchy is completely stable, maybe there's a rational explanation. And recall Newton's concern about the stability of the standard model. He was just simply wrong. The standard model is a lot more stable than he thought. So this is the first logical possibility. We should continue to think about it, but that's what it is. We don't have anything better to say. The second logical possibility is that there is a stabilizing mechanism. Maybe there is a stabilizing mechanism, very much like in the rocks. The rocks could be connected, and that stabilizes the structure, which seems to be unstable. And the third possibility is that maybe this is the wrong question. And here I would like to quote again this example of Kepler's Platonic solid. Kepler wanted to understand the motion of the orbits of the planets using Platonic solids. Now we know that this is the wrong question. This is not a question we should even answer. The radii of the planets are not fundamental numbers. This is just a property of this solar system, and in other solar systems, the distances are different. So these are the three logical options. We have either we are completely wrong, or there's a new stabilizing mechanism, or this is the wrong question. So we continue to think maybe we are wrong, but let us say a few things about the new stabilizing mechanism. For this subject, I'd like to refer you again to a talk at the Institute website by Nima Akani-Hamed. He worked a lot on this subject, and he gave beautiful talks here on the subject. What is clear is that if we want a stabilizing mechanism, it must act at energies or at distances close to the energy where the stabilization should take place. We cannot postpone this till very, very short distances. It has to be nearby, and we can actually quantify that. And if there is any mechanism, regardless of what it is, it will manifest itself as new physics at these distances. And the new physics will manifest itself as new particles that can be detected at the LHC, the Large Hadron Collider. And the leading theoretical idea for that is supersymmetry, and again, you can hear more about it in Nima Akani-Hamed's talk. This is the leading candidate for a stabilizing mechanism. Alternatively, maybe something else we haven't thought about. Maybe some other stabilizing mechanism we haven't yet thought about. So this is the possibility of having a new stabilizing mechanism. The LHC, the Large Hadron Collider, is shut down now for 2 years for an upgrade. It will start working again in 2 years with roughly twice the energy, and it will look for new stuff, whatever is there. And if it might be that it will find new particles that are associated with some stabilizing mechanism. So far, this hasn't happened. People look very carefully at the LHC and elsewhere, and there is no sign of any new particle beyond the standard model. This was the success of the standard model before. There is no contradiction, but it's also the statement now that there is no sign of anything beyond the standard model, and it might be that this is indeed it. There is nothing beyond the standard model. Perhaps the next run of the LHC will find something new. Remember, we're looking for particles that are relatively light, more or less at the same scale as the standard model, maybe a factor of 10 heavier, such that they can participate in some mechanism, maybe something we thought about, maybe something else, that can stabilize this hierarchy. In this scenario that no discrepancy is found, this is something we will know within a few years. The LHC will start working, we'll look for it, maybe they will, or maybe they will not find new particles. If they don't find anything, I think it's quite likely that there is no stabilizing mechanism. In that case, we'll have to face the third option, that this is the wrong question. So remember, option 1, our logic is totally wrong. Option 2, there's a stabilizing mechanism. And option 3, this is the wrong question. We've been barking up the wrong tree. So this is the wrong question. And here, the leading candidate is an idea called the multiverse, that our universe is actually a lot bigger than what we thought. And I'll be using the universe with capital U, or the word multiverse, for the entire universe, for the entire collection of all universes, and universe with lowercase u for our own neck of the woods. And Martin Rees gave a beautiful talk about it in Freeman Dyson's 90th birthday here at the Institute, and it's also available online. And Martin Rees is a big advocate of this picture, that the universe is a lot bigger than what we know. There are actually many universes, and the laws of physics in our universe are different from the laws of physics in the other universes. For example, the mass of the electron or the strength of the electric force could be different in the other universes. The differences could even be more dramatic. There could be different elementary particles in the other universes. Maybe this whole periodic table of elementary particles that I showed here is totally different in the other universes. Maybe it's even more dramatic than that, and in the other universes we have different number of dimensions. And then all these parameters we are trying to explain are not fundamental. They are just specific properties of our universe, very much like the orbits of the planets are specific properties of this solar system, and they have different values in another solar system. So maybe some numbers that we are trying to explain are just properties, dull properties of this universe, and in other universes they have different values. Well, if this is true, this is really, really remarkable. This is a revolution on the scale of the Copernican revolution. The Copernicus Revolution said that the Earth is not special. We are not the center of the universe. At that point, it was the solar system. We are not at the center of the solar system. The sun is at the center of the solar system. And later people realized that even the sun is not special. It's just one star in our galaxy. And even our galaxy is not special. It's one out of many galaxies. And the next step is maybe even our universe is not special, just one of many different universes. Well, obviously, many physicists, including myself, are reluctant to accept it. But we might not have a choice. And I'll say more about what choices we have. So this is the idea of the universe, and it immediately raises a lot of very interesting conceptual questions. How are we supposed to think about physics in such a setup? What are the right questions to ask in this case? The main point is that we cannot access the other universes. So is it even meaningful to ask questions about universes that are even in principle unobservable? Is this physics or not? This is being hotly debated, and every person is entitled to his own view, and this, okay, I'll leave it as that. Our universe is not special. So what selects the principles? So maybe we give up on discussing the other universes. We should at least be able to say something about our own universe. What selects our universe? Maybe we should have some selection principle that tells us why we live here and not elsewhere. So our universe might not have generic laws. The laws that we have here might not even be the most likely one. We have a distribution of laws. Are we at the generic one or at the very special one? Or are we where we are and there's nothing we can do about it and that's it? And maybe it has something to do with the fact that we are only in the only universe that can support life, and that's a tiny fraction of all possible universes. And I can talk on and on about that, but instead, I think I should start summarizing. So this is the takeaway lesson. If you slept, this is the time to wake up. We've had a long, wonderful journey through centuries of physics, starting with the Babylonians and the Greek, going to the 21st century, and maybe some glimpse of 22nd century. We said that there are two standard models in physics. Both of them are extremely successful. One of them describes physics at short distances. This is the standard model of particle physics. The second is the standard model of cosmology, which describes the universe as a whole. It is quite clear that despite the success of these models, there must be new physics beyond these models. This cannot possibly be the whole story. I've given a lot of, a lot of reasons to think so. In the words of Kelvin, there are a bunch of clouds telling us that there's something beyond that. These are the clues for new physics, and they might or might not signal a storm that is going to happen very soon. Let's hope that they do. One challenge we face is to unify these models, and this is the subject of quantum gravity, which is a huge subject. And perhaps a simpler problem is we'd like to explain all these parameters in these two models. Some of these parameters are unstable. I said that as we understand them today, if we make small changes at short distance, they make a huge difference at long distance. An ongoing experiment, the Large Hadron Collider, is going to give us input into this question. As I said, if there is a stabilizing mechanism for this instability, it will be discovered at the LHC. So this is something we'll definitely learn in the near future. So a similar talk a few years from today will tell you this is the stabilizing mechanism, or there is no stabilizing mechanism. So this is something we will know very soon, and that's exciting. So one option is that experiments will find the new stabilizing mechanism. And alternatively, if there's no stabilizing mechanism, maybe we have to go to this multiverse arena where there are lots of universes and we are just in one random universe. These parameters are environmental, and we'll have to start learning how to think about physics in such a setup. So clearly, these are very interesting issues, and we expect to have more insight in the near future, so it's guaranteed to be exciting. So I asked at the beginning of the talk, what's next? And the answer, we do not know, but it's guaranteed to be exciting. Thank you.
Thank you, Nani, for a wonderful talk. You must have set a world record in covering most orders of magnitude. 60 orders of magnitude in 60 minutes. It's a terrific job. So I would say you have also an enormous area of questions, remarks. Yes. And just wait for the microphone that we can all hear.
Thank you. Was dark energy theorized before its experiment, and if not, was that troubling?
Well, actually it was. I think it first appeared in the work of Einstein, and people like to refer to it as Einstein's biggest blunder. Einstein thought of it as an explanation for something else. Actually, I'm glad you brought this up, because it's often in physics that a good idea is invented in the wrong context. So sometimes good experimental work is done for the wrong reason, like in the case of alchemy, and this is an excellent theoretical idea that was invented in the wrong context. So Einstein wanted to explain why the universe does not expand. He wanted to explain a steady universe. And in order to do that, he invented the cosmological constant, what we call the cosmological constant, which is the same as dark energy. And then when it failed to explain the universe, he declared it as a blunder. The idea is still good, and it exists in nature. So in that sense, yes, it was theorized before. But it was still surprising. I remember the time before the discovery, there were only upper bounds on the number, and we all thought the number was exactly 0, and the question was, how can we make this number 0? So now we have a much more challenging question. The number is not 0. We have to explain why it's 10 to the minus 120. And in a way, this is a much harder question, because we can imagine that one day somebody will come with a principle that will set it to 0. Now there's something to compute. So it's very hard to imagine how we can do a calculation and end up with 10 to the minus 120.
Is it conceivable to hope that at some point in the future there will be no clouds, so we'll have some physics that will explain everything, will not have anything that contradicts it, and this will just be it?
Yep, I think the answer is yes. Whether it will be in my lifetime, probably not. But the goal is that there would be, this is unlike mathematics, where you can invent your own rules, your own axioms, and then prove theorems about some hypothetical world with your different axioms. Here we know there's a fundamental scale, this Planck scale, and once we get there, we understand that. This might take another century, maybe 2 centuries, but it looks to me like this would be finite understanding. I should qualify that by saying that even if this is the case, and we reach this goal, which might take another century or so, I'm sure there will still be lots and lots of interesting physics questions working out the consequences of these fundamental laws. What most physicists do is not go after these fundamental laws, after these fundamental questions, but they try to work out the consequences. So we understand the fundamental laws of chemistry. Is chemistry over? Of course not. There's a lot of interesting chemistry to learn. There's biology, very interesting science that needs to be done. And similarly in physics, there are many interesting, fundamental interesting questions. They are not in the sense of going after the fundamental laws of nature, but I think they are equally and perhaps even more interesting.
Hi. Is it possible that fields could be described as a geometry in which the way the fields transform is equal to their gauge transformation, and if we embed those geometries in curved space, could it be possible that a theory of quantum gravity could be obtained?
I'll be happy to discuss it with you. I think it's beyond the scope of this talk.
Thank you.
It's more, I guess, a remark than a question. So I guess there is another example of that which you called instability, which I don't remember the first name of the person, the last name is Hoyle, Hoyle. So the person who, when you look at nuclear synthesis in stars, it all kind of goes smoothly up to some point, and then there is a gap, and in order to get over this gap, certain masses need to add up in a very precise way. And there is also some many digits of...
There are many examples. First of all, let me just say a few more words about the example you mentioned. This is really a fantastic story that just by looking at nucleosynthesis and the way matter was made in the universe, Mr. Hoyle said that the whole thing does not work unless some magic happens, and the magic he needed was that a certain resonance exists in nuclear physics. And he predicted all the necessary properties of this resonance. And he predicted it not by doing any experiment and not by studying any material on Earth, just so that the theory of creating atoms in the early universe would work. I assume this is what you're talking about. And then this was a resonance of C12. And the C12 has a resonance that can decay to 3 alpha particles or something like that. And then they measured, and sure enough, this resonance that was predicted based on astrophysics turned out to exist here on Earth. This is a fantastic story. In addition to that, there are many other examples of accidents like that in science, that different numbers agree. For example, if you look at the sky, the size of the moon and the size of the sun as viewed from the Earth are more or less the same. And of course you laugh because these numbers have nothing to do with one another. These are objects of different size and they're different distances from us, and yet the angular separation by how much we see the moon and by how much we see the sun are more or less the same. That's the reason we have lunar eclipses and solar eclipses. This can happen only if they are both of them of the same order of magnitude. So there are many such accidents in physics. None of them is that dramatic. None of them is 32 orders of magnitude. None of them is 120 orders of magnitude. So there's a question, how much are we willing to tolerate? This is getting into an aesthetic question. Are you willing to tolerate 1% tuning or 1 per mil? I would say 1%, maybe. 32 orders of magnitude, I would say no. But this is more a question of qualitative thing. But thank you for the comment.
Well, it's not entirely the same. I mean, if the moon and the sun were slightly different
That's correct.
If the mass of alpha particle was, or the mass of C12 nucleus was like, I don't know, 1/100% off, then there would be no
That's right.
carbon and there would be no life.
Yep.
So
There are accidents like that. Yeah, absolutely. There are accidents like that that can affect our life. The deuteron binding energy is also an accident like that. It's very small, and that has huge consequences. There are many other examples of accidents like that. We think we know what determines this nuclear physics, and we think that this accident is a consequence of nuclear physics using the parameters that we know in the standard model. Maybe this whole idea is just a question of our ignorance, but it's hard to imagine such enormous cancellation without a real explanation. Maybe somebody will come up with an explanation. You see, in the context of this, in fact, the surprising thing about carbon is it's actually not the ground state, it's a resonance, it's an excited state that has to be at a particular value. And you can imagine that one day computer calculations become so powerful that we can actually predict that. We can calculate from first principles using the parameters of the standard model. We can check all these numbers, and this accident will no longer be an accident because there will be a calculation that gives these answers. Short of that, yep, it looks like an accident.
So you said that one of the important things was to collect data, but being a theorist, it actually didn't really tell us much about what the data were that played the crucial roles. And perhaps do you have a wish list for future data collecting for the experiments that should really be done as soon as possible?
Well, I think going up in energy, first in the LHC and then in future machines, will give us very useful data, measure interesting numbers. The first thing we hope for is that there will be qualitatively new phenomena, like a new particle, and something really dramatic that happens. Short of that, there are lots of experiments that can be done to test the standard model in higher and higher accuracy, more and more significant digits, and compare theory and experiment. Once we have a discrepancy, we can think, what does this discrepancy reflect? So I gave some numbers here. I can give more numbers, but then people will complain that the talk is too many numbers.
When you were talking about the multiverse, I was thinking of a tie shop with many different kind of ties. But thank you for explaining your tie, and the beautiful story here. You also, I think, very richly demonstrated that your presentation today is part of a much bigger kind of network of interest and discussions we have here at the Institute. And but thank you indeed for setting this kind of world record in covering so much ground. So at this moment, before I ask you to join me in thanking Nati once more, I want to invite all of you to continue the conversation in an informal way in our common room. Thank you.